Hello viewers, welcome back. In this video lecture we are going to discuss the reactions of alkenes. In the previous lecture we have discussed the reactions of alkane. As we know that the alkanes are highly inert compound because there is no reactive functional groups are available in the alkane molecule. But in the alkene, it is comparatively more reactive than alkane. For example, you see, you take this alkene, C double bond C, and like this. As you know that in this double bond, one bond is made up of sigma bond and another is made up of pi bond. Here this pi electrons, this pi bonds are not bonded tightly as we observed in the sigma bond. It are loosely bonded with the nuclei. So why these are more reactive and which can act as a Lewis base, so it undergoes electrophilic addition reaction. So here please remember that this comparatively the pi bond is more reactive than the sigma bond, because the reason is it is loosely connected by this nuclei. That's why the pi electrons are acting as a Lewis base. As a result, it will undergoes electrophilic addition reactions. Okay. Now we understood that the alkenes compound can undergo electrophilic addition reaction. Now, how this electrophilic addition reaction is going to take place? That may take in two patterns. That may occur in two patterns. For example, you see this is the p orbital. Listen carefully. These are the unhybridized p orbital. So here both the atoms can added at the same side. You see, maybe this way, that means below or the bottom, or maybe above or above the plane. Okay, so it may be either of the side. Both will occur at the same side, either by this way or by this way. If it is occur in the same side, then we call it as a syn addition. Sometimes it may be anti-addition. You see, one may be on the above the plane and another may be below the plane. You see, like this. Vice versa, it may be happen. So why? So there the addition may occur in the two patterns. One may be a syn addition and another will be the anti-addition. Syn means both will occur at the same side. Anti means one will be the above the plane and another will be the below the plane. Okay, that's all about the syn and anti-addition. Now, so far we have seen that general method how the alkene compounds undergo addition reaction. Either it may be a syn addition or anti-addition. Now we are going to see specifically what type of addition reactions can occur in the alkene compounds. Here I took first reaction is hydrogenation. Hydrogenation means adding hydrogen, especially it will occur in the presence of a catalyst, either palladium carbon, Raney nickel, like platinum, any other transition metals are required. So that is the must we should remember, and it gives the racemic mixture that we are going to discuss in detail. First we should remember that hydrogenation is a stereospecific reaction, since the two hydrogens are added to the same face of the double bond. That means the syn addition, either maybe likewise, maybe top of this above the plane or below the plane. So it may be a syn addition. So there may be two possibilities, 50-50%. It may be above the plane or below the plane. That's why I mentioned in this both cases. That's why it is a 50-50% racemic mixture. So this is a chances of 50% and this will be the 50%. So the racemic mixture that you may know that So I will post it what is a racemic mixture, that we will discuss in detail. Now, what is stereospecific reaction? To understand this topic, I already posted the video lecture that I given in the description link. Please go through that. Okay, so what is stereospecific reaction? In brief, I will tell you. It will give the exclusively one stereoisomer. For example, like 100 is to a 0. That means one isomer will form in exclusively. That means 100%. So this type of formation of isomers is called as stereoisomer, is called as stereospecific reaction. Okay. Now, so as I told you, the syn addition will take place. Both the hydrogen will added at the same side, either maybe above the plane or below the plane with equal possibility. That's why we are getting the racemic mixture. This is 50%, this is 50%. Now, let us see how the reaction mechanism takes place. So this is the catalyst surface, like either palladium, these are the solid surface. You see, this hydrogen is getting bounded on the surface of this catalyst. Now this catalyst is reacting with the alkene. First this alkene just bound to the this one catalyst surface, and this one of the hydrogen with the bond, it will connect to this alkene carbon, and finally one of that the pi bond that is connected to this catalyst surface, and followed that the second hydrogen is transferred that to complete this hydrogenation by this way, and this catalyst is getting regenerated. You see here both the hydrogens are added at the same side. That's why we call it as a syn addition. Okay. So this is the general reaction mechanism of the hydrogenation of alkene. Now this catalytic hydrogenation is a very useful method to calculate the relative stability of substituted alkenes from the heat of hydrogenation. You see that hydrogenation reactions are the exothermic reactions, so it will liberate the heat. For example, you see here we took the different substituted alkenes. You see, what is the meaning of substituted alkene? That alkene carbons are connected with other than hydrogen, that is called as a substituted alkene. You see here this alkene carbon is connected with only hydrogen, that means this is not at all substituted alkene. You see here one of the hydrogen is replaced with this alkyl. You see continuously we are replacing this hydrogen likewise. So this compound is, you see, all are R group, this alkyl groups. So this is highly substituted alkene, and this is the least substituted alkene. You see, when we are doing that hydrogenation reaction, what happens? It will liberate some heat. So that is the one they mentioned, it's a kilocalories per moles. Okay. So this is the heat liberated during that hydrogenation. This is minus 32.6 kilojoules. You see, when you compare with the substituted alkene, one of that hydrogen is replaced with some alkyl group. You see, it is getting reduced. You see, further when it is a two alkyl groups, but you see very carefully here this and this is the cis and this is the trans one. The compared to cis and the trans is always the least one. Okay. And you see when it is highly substituted, one more alkyl group has been substituted here. In the last case, all the hydrogens are replaced with the alkyl groups. You see, when the more substitution, you see that heat of hydrogenation is very less. Okay, that is 26.4 kilocalories per mole. So here you can ignore the negative symbol, that is we are using for just denoting the exothermic reaction. You see that the least number, whichever the least number, that is the most stable. You see, so this is highly substituted alkene. That means that is the most stable alkene, because it release only least energy. Okay, that's why this compound is most stable. So this catalytic hydrogenation is used to study the relative stability of substituted alkenes. I hope you understand that. In conclusion, what we learned, so the highly substituted alkenes are most stable than the least substituted alkene. That's all about this catalytic hydrogenation and its uses. So I hope you understand it. So kindly subscribe and share it if you find this lecture is useful. Thank you very much.